Hello everyone, my name is Katherine Shepard and today I'm going to be going over this week's lab for you and with you. Hopefully you can follow along with your PDF. But first I want to just go over some terms that you need to fully understand in order to do this lab correctly. So first up is light gathering power. Now just like the name says, this is basically the power that a telescope has to gather as much light as possible. So to understand this, you can think of a telescope as a bucket, and you point that bucket at your star, and you collect all the photons or particles of light that star is shooting towards us. So that might lead you to believe that if you have a bigger bucket, you might collect more light, and you'd be absolutely correct. So the light gathering power corresponds to how large your primary mirror or aperture is. This is basically how big the bucket is. So to illustrate what this does for us, if you collect more photons, you have more light from that source, and so your object will appear brighter. And as you can see from this diagram, the brighter an image is, the more of those faint stars you can see, the more clearly you can see the brighter stars, and so the more detail you can see. So that goes over light gathering power. Next, I want to go over angular resolution. Angular resolution is how small of a detail you can resolve or that you can see clearly. So in this picture, A is your lowest or your worst angular resolution, and D is the best angular resolution. Now, the key here is that angular resolution is how small of a detail you can resolve. And so to have a better angular resolution means that you have a smaller number. So A might have an angular resolution of, say, 1 arc minute, and D might have an angular resolution of, say, 1 arc second. Those are just random numbers that I came up with, but that's just to illustrate, right? A second is smaller than a minute, so you can resolve smaller, finer details with a smaller angular resolution. So I want to illustrate this again. What this means is that, say we have two stars that are right next to each other. If you have kind of a terrible angular resolution, they will blur together and just look like one kind of oblong or oval-shaped star. If you have slightly better angular resolution, you might be able to start seeing that dip between the two stars, telling you that there might be two stars there. Get a little bit better and they start to separate a little bit more. And then finally, ideally, you want to have a nice crisp image where you can get these 2 point sources and clearly see the empty space between them. So again, in this one, the top left image has the worst angular resolution or the largest number, and the bottom right image has the best angular resolution or the smallest number. Now, the next term is magnification, and this is a term that we're much more familiar with on an everyday basis. But just to illustrate, right, we have an image of Saturn here. And in this image, Saturn is really far away, it's really, really small, you can't really see anything. You can see that it has rings around it, but that's about it. We magnified it a little bit more, and you can start to see that, oh, there might be some different colors on Saturn's surface. There might be a break in the ring in the middle there. Still pretty bad quality, but much, much better than the first one. And this is a higher magnification because Saturn is appearing larger in the image. And then finally, get even bigger, we can really start to see those nice color bands across Saturn's surface. We can clearly see the delineation in the rings. This has a larger magnification than either of the two, and therefore a better image overall and the smaller of a detail that you can see. So, a larger magnification allows you to see smaller details. So in astronomy, you might have a great big field of view or a great big slab of the sky you're looking at. You might see nothing until you pick one spot, you magnify it a lot, and suddenly you can see that there's a galaxy there or there's a star there. Magnification allows you to see something that is so small that you can't resolve or see any details, and it blows it up like you're looking through a pair of binoculars or a magnifying glass. Same principle. So, last but certainly not least, is field of view. So field of view is kind of directly related to magnification. So this is an image of the Hubble deep sky. It's one of the most incredible images that we've ever obtained in astronomy. Yes, this is a real image. And all of these points of light that you see in here are galaxies. And this was taken by the Hubble Space Telescope. So let's say we want to zoom in. So we're going to zoom into this galaxy here, and we might see something like this. So my question to you is, which of these has a larger field of view? Now, I'll tell you now that the one that has the larger field of view is the first one that I showed you, or the one on the left, the Hubble Deep Sky. And you can think of this as field of view is how large of an area you are seeing. So if you have a really large field of view, then you have a really small magnification. And so then when I zoomed into this galaxy, my field of view shrank considerably. I have a much smaller field of view, but a much larger magnification, and therefore more details that I can see, and the more interesting substructures and stuff I can see. So larger field of view, smaller magnification. Smaller field of view, larger magnification. So then I just want to go over these trends that we'll see if you go back and rewatch these couple minutes. Is generally, if you increase the light gathering power, you are increasing the size of your telescope, and you're going to get a brighter, more crisp image. If you decrease the angular resolution, then you can see smaller details, and you overall have a higher quality image. So increasing light gathering power, good. Decreasing angular resolution, good. Increasing magnification, you can see smaller details, and you have a smaller field of view. So increasing magnification, great. Decreasing your field of view means that you have more magnification and you can see more details, but you can see a smaller patch of the sky. So depending on what you're doing, a larger or smaller field of view is better, depending on the science. So these are the trends that you'll see with this. These are really important. Feel free to come back and refer to this slide throughout the lab, because there are a couple questions that ask you about stuff like this. So now we're going to go into how to access the lab. This is the second lab of the semester that you need to use virtual lab for, or VLab. The last one was Kepler's Laws, which I believe was also the video I made. So this is just a quick recap of how to access VLab. You're going to Google GSU VLab. It'll be the first link that pops up. Click that. And then you're going to click the red Login to VLab button on the right. And then from there, you're going to select HTML Access. That is the right option. It gives you two of them. The left one is to download it. Then you're going to accept their terms of service, and then you're going to log in. When you log in, it is your normal PAWS or iCollege login information, and there's a little drop-down menu at the bottom. You have to make sure that you select GSU AD, or it won't let you log in. And you'll think, what, is my password incorrect? Make sure you select GSU AD. And then from there, you're going to click on the only thing on the page, which is the VLab student image. Now, pause, and remember, in my last video, I mentioned there's a little settings gear icon in the upper right-hand corner of that page. If you click on that and you have a high-resolution option, you have to enable that. Otherwise, the simulation will not work. So, double-check that gear if you don't remember if you had it for the last lab. And then go ahead and click your VLab student image icon. And then from there, you will end up on the desktop for the lab computers. So now you're going to go down to the bottom left-hand corner. You're going to click on the Start menu or the Windows icon. From here, you're going to click on Astro UNL. And then this is where it's different. From here, you're going to click on Class Action. And this will load up a really confusing menu that looks like this. You're going to go down to the bottom and click Animations. See, there are tabs down here at the bottom. Click Animations, and then you're going to click Telescope Simulator. And this is the simulator you will use. Now, make sure you can see the whole thing. So go ahead and make it full screen, whatever you want to do, because you need to be able to see all of the readouts that it gives you down here at the bottom. So now let's start going through the lab. All right, so here's your lab PDF. Same formatting as before. You have all the definitions here. It goes over light gathering power, angular resolution, magnification, those same things that I just went over with you. And then there's a cute little comic here that says, a refractor uses lenses, and so it doesn't involve mirrors, but a reflector uses mirrors, and therefore vampires won't appear in it, so it can't see space vampires. So, first paragraph goes over how to access the lab, and then there's a note that you absolutely need to use the focus adjustment slider at the top center of the focus of the page, which is this, focus adjustments, and you can slide it down until your image is nice and crisp. So, from here, you go into the lab. And for the most part, these tables are select the 8-inch telescope. The directions tell you to start with the 8-inch diameter, or aperture, and the 40mm eyepiece. So you want to come over to your simulator, go 8-inch, 40mm. And then it wants you to count the number of rays and the light gathering power. Now the number of rays is just the number of yellow lines that you see coming into the top of your telescope. And then the light gathering power is down here in the readouts box. It's labeled as LGP, and it equals, for this setting, 840, and then in parentheses it says times that of the human eye. So you'll just go through the 8-inch, the 6-inch, the 4-inch telescopes, write down the number of yellow lines, and write down the light gathering power. Fill out that nice table. And then it's going to ask you, what trend do you see? So how does the light gathering ability of these telescopes change as the aperture decreases? So how does the light gathering power, which is this row, how does it change between the 8-inch, the 6-inch, and the 4-inch? And then it wants you to look at how the brightness of your image itself changes. Now this can be kind of tricky. Just take your best guess. Does the image get brighter as you decrease the aperture, or does it get dimmer, darker? And you can think back to what I said in the opening slides. This is light gathering power. So what would happen to the brightness of the image if you decrease your light gathering power? So then moving on, you're going to start working on angular resolution. So again, it says angular resolution refers to how clearly a telescope will show tiny details. So you're going to start with the 8-inch telescope with the 40mm eyepiece, and you're going to record the angular resolution in arc seconds as given in this table. So again, 8-inch, 40mm. Angular resolution is labeled here as resolution, and it's given in units of arc seconds. So if I were to type this in, it would be 0.56 arc seconds. So that would be 0.56 arc seconds. Arc seconds is denoted as a quotation mark or 2 apostrophes. So then you just want to fill this table out. Now, in the observing box, switch from moon to star cluster and then refocus. Now, it's labeled as cluster, but it's a star cluster, so go ahead and switch to star cluster. And then adjust this slider so that it's nice and in focus. You can see as many stars as possible. So, whoops, excuse me, and my dumb little keychain. There, that's probably the best focus I can get. So, again, you're going to start with the 8-inch telescope and the 40mm eyepiece. And you're going to describe how the clarity of detail visible and the magnification of the image change as you switch from the 8-inch to the 6-inch and then to the 4-inch. So what you're going to do is you're going to start with the 8-inch telescope with the 40mm eyepiece. You're going to look at your image and see how many details you can see and how small the image is in your field of view. Then you're going to switch to the 6-inch, and then you're going to switch to the 4-inch. Does the star cluster get larger or smaller? That's basically all it's asking. And then remember what magnification is. magnification is the image getting larger or smaller. So does the magnification increase or decrease between, as you're switching from the 8-inch to the 6-inch to the 4-inch? And then it's going to ask you which telescope setting allows you to see the smallest details in its image. So does the 8-inch, the 6-inch, or the 4-inch allow you to see more stars more clearly? So then moving on, we're going to start working on magnification. And magnification depends on the focal length of the objective lens or the mirror and the focal length of the eyepiece. Now, I didn't go over this. Hopefully you've gone over this in your class. But for instance, looking at our simulation, the focal length of our objective lens, which is this big first lens here, would be all the way down here to where the eyepiece is. And then the focal length of the eyepiece is to where your detector is, or where your eye would be. Right? Because sometimes when you're looking through like a telescope or a microscope, if you put your eye right up to it, then you can't see anything. You have to kind of pull your eye away from it, find that nice sweet spot where you can actually see something. That's the focal length. So we have the focal length of the objective lens, which is labeled as O, FO, and the focal length of the eyepiece, FE. Now, don't worry about this equation. You won't have to use it for the lab. So, you're going to switch your target back to moon. So go back to moon. Make sure you've refocused the telescope so that you can see as many details as possible. This focus looks pretty good to me, so I'll leave it there. Then you're going to start with the 8-inch, 40mm eyepiece, and you're going to go through all these different combinations, and you're going to write down the magnification value. So I'm on the 8-inch 40mm for the moon, and the magnification is given as magnification equals FO over FE, which equals 35. This is the number I want. I want this 35 value. I don't want this fraction. I want 35. So then I'll go back to my table and I'll write 35. And then I'll just go through all the different options. So then number 5, which of these telescope and eyepiece combinations provides the highest and lowest magnifications? This is just which number is the highest, which number is the lowest, and what eyepiece and telescope aperture does that correspond to. So let's say the 8-inch 40mm was the one that gave me the highest. Then I would write 8-inch 40mm. That's what I would write for that answer, if that was the case. And then you'll do the opposite for what's the lowest number out of these boxes. So then for question 6, switch to Saturn. I believe that'll be easier. Go ahead and switch to Saturn. Make sure to refocus your telescope. And then, which telescope eyepiece combination provides the best viewing image of planetary detail? So, which of these, 8-inch, 40mm, 6-inch, 10mm, which of these combinations allows you to see the smallest detail in Saturn? So you just want to switch between all the different combinations and make sure to refocus each time. So see, that's totally out of focus. So I will need to refocus it. So that's about good. And then go to the 4-inch and let's go to 40mm. Tiny, can't see anything. What about the 8-inch 40mm? You're going to switch back and forth until you find the one that, when focused, allows you to see the clearest, nicest details of Saturn. So then, number 7, this is the key one. Using the information previously learned about light gathering ability, angular resolution, and magnification, justify your selection for the best telescope. So, basically justify what you said in number 6. So, remember with this one, as your light gathering ability goes up, you get more photons, your image is nice and bright. As you have lower angular resolution, you can see better details, and as you have a larger magnification, then you can see smaller details as well. So think about if I were to leave the aperture the same and adjust the eyepiece what happens to the image. Is it more magnified? Is it less magnified? How does the light gathering ability change? Does it change at all? And then if I leave the eyepiece the same and I change the aperture, how does that affect the image? And then justify using what you see happening. Like, does the eyepiece make it larger or smaller, meaning it would affect the magnification, and the aperture makes it brighter or darker, meaning it affects the light gathering power. So using those, justify what you chose. So now we're going to go over field of view. So again, set your observation to moon. So I'll go back to moon. Start with the 8-inch 40mm telescope combination and fill out the table again. So 8-inch 40mm, I'm going to refocus. That's pretty good. So then this is asking for the field of view. So the field of view value is given here at the very bottom of the readouts box. It's written in degrees. You do not have to write the unit. You can just write, say, I'm at 8-inch 40mm, so my value would be 1.22. So I would just do 1.22. That's it. And then which of these telescopes and eyepiece combinations provides the widest and the smallest field of view? Widest meaning what's the largest number in this table, and smallest meaning what's the smallest number in this table, and what combinations do those correspond to. Now, last but not least, for the simulator part, using the information from tables 3 and 4, so that's the table you just filled out for field of view, and that's the previous table you filled out for magnification. Using those two tables, how does magnification affect the field of view? Now, I said this before, so if you are completely lost or you look back at your simulation or your tables and you don't see any trends, go ahead and go back and look at my slides, because I'm pretty sure I said it. So next, you're going to go to the Wikipedia page, lists, plural, of telescopes. And you should come up with a page that looks like this. So from here, choose a telescope of any wavelength range, any location, active or inactive, historical, choose one. Choose something that you find interesting. So I'm going to go ahead and choose the first one, list of astronomical interferometers at visible and infrared wavelengths. And then I'm going to go ahead and choose the Chara array, because that's a telescope that I'm going to be working with in the future. Now I'm on the Chara arrays page. You do not choose the Chara array, you can choose whatever telescope you want. Now, use your own words. We will be checking these questions, we will be checking your answers, and if you are copy and pasting the information from online and you're not using your own words to describe it, then you will get a 0, because that's plagiarism and falls under the academic dishonesty policy set. What telescope did you choose? I would write the Chara array. Where is the telescope located? You can just look at the Wikipedia page. It says Chara is located on Mount Wilson in California. So I would write Mount Wilson, California. What wavelengths does the telescope observe? You could say this in terms of wavelength range, like the Chara array observes from, let's just say, 4,000 angstroms to 8,000 angstroms. Or you could say in terms of wavelength category. So 4,000 to about 8,000 is about the visible or optical regime. So I would say visible / optical. Boom, done. And then the last question of the whole lab, the one that's worth the most points. What are some interesting facts or information about your telescope? This can be things like historical events or important discoveries made by the telescope, instruments on the telescopes that do different things, who the telescope was named after, where you were able to find cool images taken by the telescope and what they are, And this needs to be like an essay format, and it needs to be a minimum of 50 words. If it is not 50 words, you will not get full credit for it. So I could write something like, the Chara array is the world's first and best optical interferometer operated by my advisor, Douglas Guys. I think that's pretty cool. And then I could just go on to talk about the discoveries it's made and like what I'm going to use it for my research. Basically anything that you find interesting as long as it's factually accurate. And that is the end of your lab. So hopefully that video was a little quicker than the last one. And please, as always, feel free to come to either my or Asmain's discussion sections so we can answer any questions that you may have. And with that, I will leave it there. So thank you very much for your attention, and I'll see you later.